everyone. So we will review how gravity dictates the motion of satellite and try to understand two important topics we learned. One is gravity, and second, uniform circular motion. So let's recall what is Newton's law of gravity. Newton's law of gravity says any two objects has mass. There is a gravitational force between them, and the magnitude of the force is given by this equation. G is a constant, which is 6.67 times 10 to the negative 11, and its unit Newton meter square per kilogram square will make the right-hand side a dimension for force and the unit of Newton. Now, proportional to the mass of m1, m2 multiplied together, divide by distance square. This is Newton's law of gravitational force. So imagine we can build a very, very tall tower and we can throw the object. If you don't throw it fast enough, it will get to the ground very soon. But if you throw it really fast enough, is there a chance that the object is not going to get back to the ground but keep orbiting around the Earth just like the Moon? And the answer is yes. Then we want to find out what's the minimal velocity you need to give for this object such that it becomes a satellite orbiting around the Earth. And what's the relation between the initial velocity you give here and the orbit of the satellite? And Newton's second law is dominate here. So you have the satellite. What's the force on the satellite? So we can ignore the other forces. We can just approximately think there is only one force acting on the satellite, which is a gravitational force from the Earth on the satellite pointing to the center of the Earth. Then we should have F net force equals ma, right? So the acceleration of this satellite has to be pointing to the center of Earth too. Now, if the acceleration of the satellite always pointing to the center of the Earth and is doing circular motion, which means it's a circle, and we know it's going to be a uniform circular motion, and the magnitude of the acceleration has to be v squared over r, and the direction is pointing to the center of Earth. So let's use this one to represent the direction is pointing to the center of the Earth. And it has to be given by gravitational force. The only force acting on the object is gravitational force, so it must be G, mass of Earth, mass of the object, over the distance of the object to the center of the mass. So this is the equation dominating all satellites. So let's answer the question, what is the minimum speed required for you to have a satellite orbiting around the Earth? So we have gravitational force has to equal centripetal force, and centripetal force is v squared over r. Gravitational force, on the other hand, from Newton's law of gravity, mass of Earth, mass of object, distance of the object to the center of Earth, this Fg, has to equal mv squared over r, right? And we can see this m and m cancel on both sides. We solve for v. So how it works? M and m cancel, and this r would cancel this power of 2 here. We can solve for your v is g me over r. And r should equals to radius of the Earth. You can just replace by radius of the Earth. Now we just need to plug in the numbers. G, capital G, 6.67 10 to the negative 11. Mass of the Earth, 5.97 times 10 to the 24 kilogram. Radius of the Earth, 6.37 10 to the 6 meter. Everything there. We find a 7.9 thousand meter per second. That's the minimal speed for a satellite that you launched that can orbiting around the Earth. And then we have another special case of satellite, geostationary orbit, which were relatively stationary over the surface of the Earth. And we all know that the Earth spins in one circle in one day, which is 24 hours, right? So the satellite, geostationary satellite, has to be orbiting around the Earth in one full circle in one day as well. So the period, we call the period of the satellite to be 1 day, which is 86,400 seconds, roughly. And we want to know what would be the orbit of this geostationary orbit. And we have an equation to find out velocity and the orbit. Now we want to find t. But we do know t and v are related. Period should be the circumference of one circle over velocity. So we still should have gravitational force equals centripetal force. And now I can replace my v by 2 pi r over t square over r. So it's become an equation of t and r. Now, gravitational force also should equal g times me m r squared. M and m cancel. Now we need to solve for r. We find r cubed should equals to g m e t squared over 4 pi squared, which is entirely derived from this equation. You can try to check whether I get this one right. So which tells us okay, the rest is simple. We just need to plug in all the numbers. What is G, what is ME, what is T, and after the calculation, we find out R is 4.22 times 10 to the 7 meter. And now recall the radius of the Earth is roughly 6.4 10 to the 6 meter. So what's the distance we need to bring the satellite to space? Fun is roughly 6 times the radius of Earth. So we need to send this satellite. This is 1, 2, 3, 4, 5, 6. So roughly you need to send your satellite 6 times RE to space, so it becomes a geostationary satellite. So let's do one homework example. So we know the orbit is 7.8 705 kilometers above the Earth's surface. So we want to know the period. So which equation we should use? We should, of course, use Fg equals mv squared over r. Fg is g me m r squared m 2 pi r over t give me v squared, right? V, and it's square over, this is r, this is not v, this is r. And then I need to solve for my t. Solve for my t from this equation. Solve for my t. I find the solution should be 4 pi squared r to the cube g me. Putting in all the numbers, I find that the time is 5.93 times 3 seconds. And now it's your job to find it into, convert it to hours. 5,930 seconds converted to hours. Okay. Next question, the speed. Now it's relatively simple after you find the period, right? So, and we know the orbit. We know the orbit. Of course, the one thing that I want to point out here, this r you should use in this equation. This is re, and what it gives in the problem is, let's call this one a. Let's call this one h. Let's call this one h. And our r in this calculation should be re plus h. And re is 6.37 10 to the 6 meter, and h is, from the question, 7.05 10 to the 5 meter. If you add them together, it's actually my r is actually 7.07 times 10 to the 6 meter. So that's the radius we should use to calculate t. Now after you find the t, finding velocity is, finding speed is simple. V should be 2 pi r over t, and of course r is radius of Earth plus orbit height, which is from the satellite to Earth's surface. Plug in all the numbers. This is my r over t meter per second.